Okay, so now we have another sum, again a university question of distributed loads. So as you can see here, we have loads or forces acting in negative y direction. These distributed loads are acting in positive y direction, and we also have a moment at point B. So we have to find the resultant for this system. To begin with, let us simplify the diagram that we have. For this particular portion, we can convert this distributed load into a point load or a concentrated load. What we can do is, we can see this resembles like a triangle, so we can use the area of a triangle formula. So our F would be equal to half the base, which is 6, and the magnitude of force, which is 30. So this will come out to be as 90 Newton. This is a linear force. So this force would be acting, this is total 6, and the magnitude varies from 0 to 30 linearly. So our force would be acting at some point between A to B. This point would be 2 meters to the right. The other distributed force is here. It resembles a trapezium. Suppose it is something like this. So what we can do is, we can convert this trapezium into a rectangle and a triangle. So now we can look at this system as combination of two systems, two distributed load systems, and we can simplify them. So first we will take the rectangular part. So suppose this is F1, so our next, this portion is F2, and this would be F3. For the calculation of F2, which is this highlighted portion, the force here is, at the beginning we have 9, then the 9 is the distance, and the force at the beginning is 10 kilonewtons per meter. So the entire total force would be again 90 newtons. Here the force is acting downwards, so it will be this way, and here this force will be acting upwards in the positive y direction. The remaining portion is again resembling a triangle. So for this again we use, which is a right angle triangle. So we'll use that area of triangle formula, which is half into the base, which is 9, and the total force here is 30 kilonewtons per meter. For this we have already used 10, so the remaining portion is 20 kilonewtons per meter, so we'll use 20 here. By solving, we again get 90 kilonewtons. So now we have a simplified version of this complicated diagram. So we can now look at the resultant, or the simplified diagram would be something like this. So this is our simplified diagram. There are no forces acting in x direction. What we also have at point B is a moment of 225 kilonewton meter. Now we have to find a resultant of these forces. So for this, since there are no x component here, we can directly write resultant. This force acting downwards should be taken as minus 90. The other two forces are acting upwards. So this will be plus 90 plus another 90. So our total resultant force would be. Now what we also have to see is the moment. Generally, the moment is solved about a single point. So for our reference, we take our point as point A. So for point, So we can give it as moment about point A is given as this moment is in anti-clockwise direction. So we'll see the conventions here. For anti-clockwise direction, the moment is taken as positive, and for clockwise direction, moment is taken as negative. This is the convention that we are going to follow. This 225 is in anti-clockwise direction, so it is taken as positive, so we get 225. Now we are finding, now understand, we are finding the overall moment of the system about the point A. At point A, if we consider this force acting on point A, with respect to A, it will cause a motion in this direction. This is a clockwise direction at a distance of 2 meters from A. So this will give us a moment of minus 90 at a distance of 2 meters. So we will not mention the units here. So we will say 2. The other two forces, this force of 90 newtons and this force of 90, actually this is 90 kilonewtons. So these two forces are acting upwards, that is, they will cause a motion in anti-clockwise direction, both these forces. So these forces will be taken as positive, so we get 90. For this force, the overall distance would be 6 meter plus 4.5, which is 11.5 meter. And for this force, an addition of 1.5, so this will be plus 90 into 30. So this will be our overall moment about a point A, and this will give us a value of 2070. Also, the value comes out to be positive, so this indicates that our moment is in anti-clockwise direction. The unit is kilonewton. For our understanding and for convenience, we take a point at some corner. Suppose we are finding a moment in the exam. We have a question where suppose we have to find moment about C or moment about point B or some intermediate point. Suppose here say point D, which is equidistant from these 2 points of 4.5 meter. The value of forces would remain same, but the d, which is the distance as we saw in Garrigan's principle, this distance will keep on changing, and the overall answer, that is the resultant momentum, would remain to be same. So this is an entire university question which will come for 10 to 12 marks. So it's a very important question. We have covered all the concepts here, right from here we have distributed nodes, concentrated 1 point node, we have converted them. We have seen example of combination of distributed nodes. Here we had a trapezium. Then moment, how to solve moment, the conventions of x and y axis that we saw in the last sum. So this would be pretty much sufficient for you to do well in your exams.